For these next couple, I just want to list the number and type of solutions. So essentially, I'm looking at the discriminant, which is just the piece of my quadratic formula that's under the square root, the b squared minus 4ac. So when I apply that to this first one, that's going to be a 6 squared minus 4 times a times c. And that's going to be a 36 minus 32, which is a 4. When I get a positive number that's a perfect square, like a 4, it means that I'm going to have two rational solutions. For the next one, I do the same thing. I do the b squared minus 4ac. So I end up with 16 minus 16, which is 0. When my discriminant is 0, it's telling me that I'm going to get one rational solution. I do the same thing with the next one, the b squared minus 4 times a times c. That's a 9 minus 20, which is a negative 11. When I get a negative for my discriminant, it means I have two complex solutions, because essentially I'm going to be taking the square root of a negative, which means I'm going to get imaginary solutions. And really, there's only one option left. I have two rational, one rational, two complex. The only other option, that's what number 23 is asking me about, would be to get two irrational solutions. And you get two irrational solutions when the discriminant is a positive number that is not a perfect square. Okay, for example, something like, I don't know, a 23. Okay? For this one, we want to find the vertex, the x-intercept, and the x-intercept of the quadratic. Then we want to interpret what it means. So to find the vertex, we just do the opposite of b over 2a. So that's going to be a negative 4 over 2 times a, which gives me a negative 2. Now that's just the x value for my vertex. I have to plug it back in to get the y value for my vertex. So I plug that negative 2 back in. And when I do that here, I get a 4 minus 8 plus 4, which is 0. So my vertex is negative 2, 0. And then it also asked me to find my x-intercepts. The x-intercepts is when I set y equal to 0. So essentially, when I set this equation equal to 0 and I solve for x, here I can factor this. It factors in x plus 2 times an x plus 2. I set each factor equal to 0. And really, I only need to do that once and find out that x equals a negative 2. So my only solution here is negative 2, which think about that as an ordered pair, is negative 2 comma 0. So when I've got plugged the 0 in from y. So when I look at this, my vertex and my x-intercepts are exactly the same. So when it asks us to interpret this, it just wants us to realize that this is a parabola where the vertex and the vertex and x-intercepts are the same, which means it's a parabola that looks like this. Okay. It's a parabola that has multiplicity of that one solution. So instead of passing through the x-axis, it only touches the x-axis. Okay? So understanding that that value can be shared here, which means we have a parabola that looks like this. Okay? For this one, it asks us to solve each of these, and we're going to solve this by factoring. So I'm going to solve this by factoring. Essentially, I'm going to solve this as an equation first, and then we'll look at the graph at the end. So I'm going to solve this equation. I build a bridge. That gives me an x plus 6 and an x plus 2. So I get two answers, a negative 6 and a negative 2. And then essentially what I do is I plot these on a number line and decide whether I'm going to shade inside or outside. Okay, so I'm just going to choose another value here. I'll choose something over here like a 0. If I plug a 0 in here, I would get a 12 is less than or equal to 0, which is a false statement, which means instead of shading out here where 0 is, I'm going to shade inside these two values. And since there was an equal to condition, I'm going to put close dots here. So really, the graph that I have is the graph of negative 6 less than or equal to x less than or equal to a negative 2. Essentially, I'm establishing whether or not this is an and or an or inequality, and I do that by looking at the graph. So this is the solution to this quadratic inequality. I do the same thing with the next one. Again, I ignore the fact that it's an inequality for a moment. I build a bridge and I do my factoring. That's a plus 4 and a minus 1. Factors into these two values, so I get x equals a negative 4 and x equals a positive 1. And now I throw these on a number line. And I plug in a value, and I would probably plug in something like 0 again. When I plug that in, I get negative 4 is greater than 0, which is a false statement. So instead of shading in here where 0 is, I shade out here where 0 does not exist. So I get something that looks like an OR inequality. Again, I get open dots here because there's no equal to condition. So when I write the solution, I want to write it as an OR inequality. I want to say that x is less than a negative 4, or x is greater than a 1. And those are that's my solution set. For the next one, it asks me to simplify this expression, so I'm just doing some multiplication, so I'm distributing the 2x. When I do that, it gives me a 2x cubed plus 4x squared minus 8x. Then I distribute the 1. That gives me an x squared plus 2x minus 4. And I simply combine like terms, which leaves me with a plus 5x squared here, a minus 6x, and a minus 4. Sorry, I almost couldn't read my own handwriting there. I believe that's a minus 8x. Okay? The next one, if we want to square this thing, that means we're doing it 4x plus 5 times itself. And when you do that, you have to FOIL this out. You have to multiply it out. You can't just square each piece. You got to distribute here, which gives me a 16x squared plus 20x plus 20x plus 25. And if you just square each piece, you'll end up with the first term and the last term, but you'll miss these two in the middle. And those two in the middle are kind of important because they give us a 40x. Okay, so make sure you multiply it by itself. For this one, I want to do division here. And if I want to divide these two, I'm going to use synthetic division. So I take the opposite of this guy and put it inside my box, negative 3. Now I have to write down my coefficients in descending order. So like here I have a 1, a negative 10, and a 7. But I'm missing the x squared term, so I have to put a 0 in its place. So 1, 0, negative 10, 7. And now I bring down this first term. I multiply, I add straight down. I multiply, I add straight down. I multiply, I add straight down. So what this interprets into is I start with an x cubed. Now I'm going to have an x squared, so it's a 1x squared minus 3x minus 1 with a remainder of 10. And the remainder I put over the thing I was dividing by. Okay. Later we'll use synthetic division to check solutions and hope to get a 0 for my remainder. For this guy, we just want to state where this thing is increasing, decreasing, any relative maximums and minimums. So increasing, decreasing, we always go left to right. So here, the function is heading downward as I go from left to right. Then it starts going back up again, and then it heads back down again, and then up again. All right, and when the function is going up, it's increasing. When it's going down, it's decreasing. So in other words, from forever until I get to this value, it was going down. So from negative infinity to negative 3, it's decreasing. And then from here to here, it's also decreasing. So these two values. So from 0, sorry, I didn't draw that quite long enough. From 0 to 3, it's decreasing. So from 0 to 3, it's decreasing. And then it's increasing from the negative 3 to 0. And then it's also increasing from the 3 to infinity. And I just put union symbols in between here to say it's increasing on each of those intervals and it's decreasing on each of those intervals. And I'm using interval notation. For relative maximum minimum, I'm just identifying these as ordered pairs. So I've got a relative maximum right here at 0, 0. I've got a relative minimum right here at negative 3, negative 4. I've got a relative minimum here as well at 3, negative 5. And it's okay to have more than one relative maximum or more than one relative minimum. They're just maximums or minimums relative to the points around them. Okay? End behavior, I'm always looking as x goes to negative infinity, and then as x goes to positive infinity. And really, that's just a fancy way of saying, look at the far left of your graph. The negative infinity is looking at the far left right here. What's the function doing? Well, it's going up, so my f of x is going up. It's going to positive infinity. And then the x going to positive infinity is saying, hey, look at the right side of your graph. What is it doing? It's going up forever, so f of x is going to positive infinity once again. And that's my end behavior, okay? And that's how I have to denote it. For this one, if I wanted the end behavior algebraically, when we're in standard form, I simply take the highest degree term here, which is this guy, and I plug the positive and negative infinity in. And really, this just becomes a game of signs here as I plug this thing in. So I'm looking as x goes to negative infinity, and then x goes to positive infinity. If I plug the negative infinity in, essentially I'm doing negative infinity to the 6th power and then times the negative 2, which is negative 2 times a positive, which is a negative. So when I plug the negative infinity in, I get a negative infinity out. And that's it. That's all we're doing here. Okay? I do the same thing with the positive infinity. I plug a positive infinity in here and see what I get. That gives me a negative 2 times a positive, which is a negative. So f of x was a negative infinity once again. So that's my end behavior for this one. Okay? Scoot those over. The next one I'm doing the same thing, except this time it's not in standard form, so I have to plug it into each. But I'm still doing the same thing. I'm still doing x going to negative infinity, and then x going to positive infinity. And I'm just plugging them in. So I've got a negative x squared times x times something squared. And I plug the negative infinity in. And really, I'm just seeing what the sign is going to be. That gives me a positive times a negative on the outside. This is still a negative. This one becomes a positive when I square it. So I have negative times positive, which is a positive. So that's the first piece of my end behavior. When I plug the negative in, I got a positive out. And I would do the same thing with the positive infinity. I've got a negative x squared times this guy times something squared. I plug the positive infinity in. That gives me a negative infinity times a positive times a positive. So I've got negative times positive, which is a negative. And that's it. Number 33, we're going to use the end behavior to sketch a quick graph here. And the first thing I want to do is set each of these guys equal to 0. So I do the x equals 0. I do the x plus 5 equals 0. And I do the x minus 2 equals 0. Here, this one's already solved. I get x equals 0. Here, this one I subtract the 5, x equals negative 5. Here, this one I add the 2, I get x equals 2. So these are my x-intercepts. Got this guy here. Got the negative 5 is back here. I've got the positive 2 up here. And now I just have to look at multiplicity. Since that was an x squared, it means that this x equals 0. I would actually get that solution twice. So that would have a multiplicity of 2. This one I would get once. Since the x minus 2 is squared, I would get that solution twice. And really, the multiplicity tells us whether we're going to touch or pass through. If the multiplicity is even, we just touch. So we're just going to touch at this x value. If it's odd, we pass through. If it's even, we touch. So that really helps us in terms of drawing this graph. The only other thing that will help is our end behavior. I need the end behavior here. So I look as x goes to negative infinity. And when I plug that in, that's going to give me a negative infinity. And then I look as x goes to positive infinity. And when I plug that in, I get a positive infinity. And so what that tells me is that this end of the graph should be headed down. This end of the graph should be heading up. And now as I start to graph this, I have to be going this way. As I approach the negative 5, I want to pass through because the multiplicity told me so. At the 0, I just want to touch. At the 2, I just want to touch. And then I have to continue up forever. And so using the multiplicity and the end behavior, I can draw a quick sketch of this thing and immediately kind of see where the relative maximums and minimums are going to be. And that's it.